Hello. So here we will take one example where say a feedback counter system is given. A feedback counter system is given where this is forward path gain, this is sensor gain, and the forward path gain transfer function is given like this: k into s plus 4y, s into s plus 10, and h is sensor transfer function is given by 1 by s plus 20. Now question is that we have to find out the range of values of k for which system will be marginal stable, and if this is marginal stable then find out the frequency of oscillations. So how we have to find out? First of all, answer is like this: you have to find out the characteristics equations. What is this? This is 1 plus gshs equal to 0. That means here we see 1 plus k into s plus 40 into s plus 10 into 1 by s plus 20, that is equal to 0. That means you see s into s plus 10 into s plus 20, right, plus k into s plus 40 equal to 0. This is your characteristic equations. Now if you solve this, what you will get? You will get k plus see s cube. This will be s into s square plus we see 30s plus 200 plus k into s plus 40k equal to 0. And uh, see, this is your s cube plus 30 s square. I see that is 200s plus ks, that is 200 plus k into s plus your 40k equal to 0, right? So this is the uh, characteristic equation. You see, from the characteristic equations you have to find out the Routh array. I will form the Routh array with a similar procedure we have learned, so you can do it of your own. Now this is your characteristics for an email. So s cube 1 200 plus k, this is, and this is s square, that means 30, and this is your 40k. So you divide this by 10, you get 3 and 4k. So 3 into 200 plus k, that means 600 plus 3k minus 4k by 3 and 0. This is this into this minus this into this divided by whole this. So this will give 4k. Now your aim or the question is that the find out you have to find out the value of k for which system will be marginal stable. So again the question comes, if the system has to be marginal stable, then all the elements of a particular row has to be made 0. That means this is having one element other than the last, other than last row. So this is 0. If you make this equal to 0, that means 600 minus k by 3 equal to 0, you get k is equal to 600. The value of the gain can be adjusted to 600 such that the system will be marginal stable. And if the value of k is equal to 600, so this will be equal to, let's see, all the elements become 0. This will be 0, this will be 0. So s to the power 1. This is the s to the power 1 containing row which will be having all the elements 0. So system will be marginal stable. So in this case, this will be marginal stability, right? Next, once this is marginal stability, that means all the elements are 0. What you have to do? We have to consider the previous row. So auxiliary equations will be equal to 3s square per 4k s to the power 0, and the value of k already calculated 600. So auxiliary equations become 3s square plus, you see, 2400. Now already it has been given that the system is marginally stable, so you don't need to have calculations. The next step, like differentiation, is not required. What you have to do? You have to find out the frequency of oscillations. That means you have to make as is equal to 0. So if the value of as is equal to 0, you get this 3s square plus 2400 equal to 0. So s square is equal to minus 800. So s is equal to plus minus root over minus 800. So plus minus 10 into 2 root 2 j. So you get plus minus j 20 root 2, and in order to get the frequency again, this will be tallied with this. S is equal to plus minus j omega, so you get omega is equal to 20 root 2 rad per second. Okay, so this is the frequency of oscillations, and all again we have proved that the poles are located on plus 20 root 2 minus 20 root 2, that means on the imaginary axis. So that means the system is marginally stable. So these are the basic concept by which using this you can do any kind of solutions for any kind of problem, margin stable, unstable, system stability, whatever you want to get from using the Routh array analysis. And the special cases you have to keep in mind. So next, definitely I will give some you see, that is known as assignment based upon this. So basic assignment is that I will just give one characteristic polynomial, or question assignment 1. You see, a QS I will just write down, and you have to find out the value of k for which system will be stable. That is simple example. QS is given by s to the power 4 plus s square, sorry, s cube plus s square plus s cube plus s square plus s plus k equal to 0. So you have to find out the value of, find the range of values of k for which the system will be stable. So during getting the solution of it, you may have to cross the or to overcome the issues of special cases, like there may be like the situations where there may be the any row, all the elements may be 0, so you have to consider the auxiliary equations. It may be possible that the pivoting of the 0, that means any row containing only the first element 0 but rest of the elements are present. In that case, you have to consider that epsilon and so on. By considering all these special cases and rules already discussed, you have to just complete the Routh array. From the completed Routh array, now taking all the elements positive as to make the system stable, and from that you can get the value of k. Okay, so that is the end of this chapter, and in the next lecture onwards we will discuss about the Routh-Lucas analysis. Next sections we will discuss the Routh-Lucas analysis. Just a brief analysis of the Routh-Lucas analysis. That means I would like to say what is Routh-Lucas means. Say so far we have discussed the characteristic equations, and the roots, the positions of the roots have not been actually discussed. That means it was not possible to find out the roots of the characteristic polynomial by using the Routh array, but we have found the system is either stable or unstable, or number of roots on the left hand side of the S plane or right hand side of the S plane or on the imaginary axis, that we have discussed. But how the roots can be varied, maybe roots are initially located in these positions, right? So maybe there is a value of k gain which can be varied, like knob. This can be used as knob, or system gain can be such a varied such that this pole may shift from these locations to this location to this location to this locations, or this pole may shift to this location to this location to this locations. That means if you vary the gain, you see the range of values of k for which the system was stable. For example, in the last example, you see there is a value of k which was 84 by 25 for which the system was marginally stable. That means there was the value of k, so 25 and 0. You see, you can remember, so the value of k was 0 to this. Within this range the system was stable. That means if the value of k is varied between 0 to 84 by 25, that means the system poles are so left hand side of the S plane, right? So maybe the pole is here in this region, and once the k is varied to k is equal to 84 by 25, so this pole may be there, where, but once the k reaches 84 by 25, this is on the imaginary axis. And if the value of k was greater than 84 by 25, what was there? The system was totally unstable. That means what? That means the system pole reaches to the right hand side of the S-plane, isn't it? That means from the basic concept of Routh array, what we see, if the gain is varied by certain amount, system pole may move from left hand side of the S-plane, to the imaginary axis to the right hand side of the S-plane. There may be movement, and how this movement is done, and if the poles are shifted from one position to another position by varying this gain k, that method is very important method for designing of any control system. That is a very classical method discovered by Evans. So this analysis plays very important role for any control system engineers. Okay, so in our next class onwards, there will be some lectures where we will discuss the detailed procedure of how to get the Routh locus, and what is Routh locus, and what are the different procedure to find out a Routh locus plot for any system. Okay.